My name is John Hinlsey, and it's my pleasure to present my research on epoxy toughening for self-healing via optical fibers. I am a member of the Multifunctional Composites group here at NC State under the supervision of Dr. Patrick. My research on fiber-reinforced polymer composites is motivated by their diverse applications, their high stiffness and strength-to-weight ratios, their corrosion resistant, and their fatigue resistance. However, structural composites are susceptible to internal interlaminar delamination. This is when the different layers of the material debond from one another and simply come apart. And this is very hard to detect because it occurs inside the material itself. A solution to this problem is to develop a self-healing composite that utilizes both microvascular channels and polymer optical fibers. So when damage does occur in the composite, the networks and the optical fibers fracture, releasing healing agents and light into the crack. And through photopolymerization, the healing agent hardens and self-healing occurs. My objective is fracturing optical fibers for targeted light delivery in the crack plane. Optical fibers have both a core and a cladding. The refractive index of the core is higher than that of the cladding, so total internal reflection can occur. Thus, light can transmit from one end of an optical fiber to the other. We first tried using silica fibers, but they were just too strong, and they bridged the crack during testing. Then we used polymer optical fibers, and they can be tuned to fracture at the desired crack plane. We use a mode 1 fracture evaluation to evaluate the healing efficiency by using a tapered double cantilever beam, or TDCB for short. The TDCB is crack length independent due to its special tapered geometry, meaning we can find the fracture toughness, or K1C, using the constant alpha and the average peak loads without having to measure the crack length while we test. And just to be clear, the challenge that I'm facing is to fracture the optical fibers for targeted light delivery to the crack plane. We hypothesized that we can increase the fracture toughness of the polymer matrix, and if we do that, it will allow the optical fiber to fracture at the crack plane. We have achieved toughening by blending the brittle epoxy matrix with a ductile toughening agent called CTBN for short, and the results show a linear increase in mode 1 fracture toughness with increasing CTBN content. And this is where a 10% loading results in consistent fracture of the polymer optical fibers in the crack plane. Future studies will investigate optical fiber light transmission through opaque modified matrices, fabricating toughened epoxy TDCBs with microchannels, and achieving in situ self-healing. To end, I'd quickly like to thank the NC State RISE program and the Air Force Office of Scientific Research for funding, and my fellow members of the Multifunctional Composites group, especially my graduate student mentor, Sharif. Thanks for your time, and I'm happy to answer any questions.